afternoon, students. Today we are going to studying about the Maxwell inductance bridge. By this bridge, we find the value of the unknown inductance. So let us start. There is a journal arrangement for the Maxwell inductance bridge. It contains a R1 and R2. These are the pure resistances. And here Rx and Lx are the values. These are the unknown values. And here R3 and L3, these are the variable quantities. So there is a detector denoted by D, that is between the terminal B and D. Here is a battery which is also connected between another two terminal A and C. There is a tapping key that is denoted by K, which is used to open and close the circuit. So here we have to find the value of Rx and Lx. Rx is the unknown resistance and Lx is the unknown inductance. So when we start the terminal, then there is a flow of current that is denoted by I. When this current reach at point A, then it splits into two parts by Kirchhoff's current law. That is, first one is I1 and second is corresponding to R2, that is I2. And when this current again goes from here to this point, then it again split into two parts. That is, first one is ID, and at this point that is IX. And you know very well the value of IX is equal to the I2 minus ID, that is the IX current. When this current goes from here, then it becomes I1, and when it reaches at this point, then it becomes I3. The value of I3, which is I3 equal to the I1 plus ID. This is the values of the currents. So now when we satisfy this balanced condition, when potential at B is equal to the potential at D, that becomes the balanced conditions of the bridge. Then by this balanced condition, it becomes the impedance across A to D and impedance across B to C by multiplying both impedance, that is equal to the impedance of A to B and impedance of D to C, both are equal. So by giving the name of the impedance, that is A to B, that impedance Z1, and impedance from A to B, that becomes impedance Z2, and impedance from B to C, that becomes impedance ZX, and from C to D, the impedance becomes Z3. When we vary the values of the R3 and L3 till when the value of ID becomes 0. When ID equal to 0, that means this is the balanced condition of the bridge. When this condition becomes ID equal to 0, then the potential at B is equal to the potential at D. Then the equation for the balanced bridge becomes Z1 into ZX, Z1 into ZX, the impedance of A to D across R1 into impedance of B to C across Rx and Lx that equal to the impedance of A to B, that is Z2, and impedance from D to C or C to D across R3 and L3, that is Z3. So gives the name of this equation 1. Now we have to find the values of Z1, Zx, Z2 and Z3. So here the value of Z1, that is equal to the known resistance and pure resistance are 1 are 1. Similarly, the value of Z2, similarly the value of Z2, that is the pure resistance, are 2. That is the pure resistance are 2. Now, similarly, the value of impedance Z3, that is equal to the resistance R3 and inductance L3. As it is write down R3, but there is a inductor and inductor have their own internal resistance, so we can write it here omega L. Here omega is the angular velocity of the source and L3 is the inductance of this inductor. This is the real part and this is the imaginary part, so we can write it plus j omega L. How we can take this value j omega L3? This becomes by the phasor diagram and phase angle of the circuit. So we can write it as the whole under root of R3 का square plus omega L3 का square. But in case we only take the value of Z3, that is equal to R3 plus j omega L3. So similarly we can find the value of the Zx. Here Zx is the impedance and across Rx and Lx. So we can write Zx is equal to this value of Zx is equal to Rx. Similarly, like Z3 with Rx plus j omega Lx. This came from these lines. Now, by putting these values in equation 1, it becomes here put Z1 into Zx. Here value of Z1 is equal to R1. So write here R1 into Zx, where Zx is equal to Rx plus j omega Lx. Rx plus j omega Lx, bracket close, and equal to Z2 into Z3. Here value of Z2, that is equal to R2 into Z3. Z3 is the value R3 plus j omega L3, bracket close. Now multiply by R1 in bracket and by R2 in this bracket. So it becomes R1 into Rx plus j omega Lx R1 is equal to R2 into R3, R2 into R3 plus j omega L3, j omega L3 into R2. So now separate the real and imaginary part. So here R1 and Rx is the real part, and here R2 and R3 is the real part. So it becomes R1 into Rx बराबर है R2 into R3. Now here we can find the value of unknown resistance, that is Rx, that is equal to Rx R2 into R3 divided by R1. So this is the value of the unknown resistance. Now similarly we can find the value of the unknown inductance from this imaginary part. So imaginary part is j omega R1 Lx and j omega R2 L3. So write down here omega R1 omega R1 Lx, which is equal to omega R2 L3, which is equal to omega R2 L3. This omega cancel by this omega, and it becomes R1 Lx, which is equal to R2 L3. Now we can find the value of Lx from this equation. So Lx is equal to R2 into L3 divided by R1. So this is the value of unknown resistance, and this is the value of unknown inductance. So by this we can find the value of unknown inductance with the help of Maxwell inductance bridge. Thank you and stay home, stay safe. Jai Hind.